Is the recording doing anything? Yeah, we are recording. How cool is that? And now I think I head over to, I'm on the big computer. Well, the big computer, it's still a laptop, but it's not a tablet. And actually that works quite well, actually. Okay, share the content. What do I want to share with you? I want to share with you this one here. Right, can you see the screen? Wonderful, and it seems to work. And Bernardo, here's your cue again. I know that you've just posted it, but please don't forget to record your attendance in Moodle. Thank you, Bernardo. Brilliant. And what makes me truly happy is that quite a number of people are in this session here. That means that you guys obviously have received the link and it's in your team's calendar. Is that right? So it looks like the system works somehow. Good. No, that's brilliant. Task 3. What is task 3? Let me think. It is about the binomial stuff. Task 1 was counting the numbers. Task 2 is actually doing the Poisson, and I want to do something with that today again, because there were some people who were not quite sure about it. And we are going to do the binomial, so you should be able to do task 3 hopefully after today, if you really must. But you've got plenty of time. The deadline for the entire practical, I think, is the first week after the end of term. And let's make a start. So welcome, everybody. Let's just simply do a quick revision of what we tried to do last week when we introduced this Poisson distribution, and we said the Poisson distribution is relevant. Poisson distribution is relevant when we have, let's say, rare events in a given time or volume or, let's say, number of plates, all these things. And what we have here are count data. So that's very important. We have count data. And I think the easiest way is just simply by giving you an example. And this Poisson distribution is really important, although it's not taught very often. And I don't really understand why this actually is the case, because it's conceptually not terribly difficult. So we can use that if we've got, for example, colonies bacterial or other colonies on plates. For that, we could easily use and happily use, with plates, I mean petri dishes, for example. They are usually referred to as plates. So colonies on a petri dish, something like that. Interestingly, a little bit of history, the Poisson distribution was actually developed in order to find out how many people in the Prussian army every year die because they are kicked by a horse. So now you know why people are interested in that. It certainly is a rare event. We have count data, and it is a given time span because you looked at it per year. Horse kicked by a horse per year. So we could do colonies on a plate, or I want to do a little bit more, say, realistic. And I share a secret with you. One of my many weaknesses, and don't judge me, okay? I don't want any comments that this is gross or what you prefer or anything like that. This is just what I like. I absolutely love cinnamon raisin bagels. Okay, now I said it, okay? Cinnamon raisin bagels. I love it. For breakfast, there is, hardly anything that beats it. Okay, so I'm not totally weird, or at least Emily and I are weird, but do you agree that we are weird or that you like them? Okay, so cinnamon raisin bagels. And the important thing for me is really fantastic. That's great. The really important thing is the number, and I abbreviate it like that, the number of raisins. The number of raisins per bagel. And I know that there are people out there who don't like raisins. My son absolutely hates them. But, that's fair enough. So, for me, the important thing is the more raisins in the bagel, the better. And my wife, who I'm incredibly grateful for, doing all the things that keep the family going, she provides me with a steady supply of these cinnamon raisin bagels. It's a little bit to the detriment of my figure, but hey, it's lockdown. Who cares about these things? So I get my cinnamon raisin bagels for breakfast, and I am a very happy man. And of course, I want to know what is the average number of raisin per bagel. So what I do is actually I can count the raisins per bagel. So I can say, right, in one bagel, I found 5. In another one, I found 7. And in the third one, I found 8. And I want to actually know how many bagels can I expect in this particular brand of bagels? So here, this is my sample. And I counted 3 bagels. So 3 bagels. And what I want to know now is how many raisins can I expect from this particular supplier. And that is exactly where this Poisson comes into play. So how many raisins have I counted in these 3 bagels? That's very easy. I just simply add them up. So we've got 5 and 7 is 12 plus 8. That gives us 20 raisins in 3 bagels. Okay, so we've got 20 raisins. Edith, my daughter loves pineapple on pizza. People are different. Raisins, pineapple, you know, God knows what. Pickled gherkin with Nutella. Whatever makes people happy. So, you see. And I'm not disputing that. So, 20 raisins in 3 bagels. And what I want to find out is how many raisins can I expect in these bagels from this supplier. So let's head over, and I'm going over to share a different screen. So let's share the other screen that I have already. Where is it? Here. And can you see the screen again? Okay, good. So here is this calculator with the count data, this Evan Miller calculator, right? And we can use that, and we can just simply say, so this sample 1 here, these are my bagels. This is this particular supplier. And I observed 20 raisins, that's the number of events, 20 raisins in actually not days. The bagels don't last very long. There are not many bagels left after a day, but we have 20 bagels in 20 raisins in 3 bagels. So 20 raisins in 3 bagels that I observed. And what I get now is this confidence interval. It is 4.1 to 10.3. You see that here. That is what this calculator tells me. The 95% confidence interval for the number of raisins per bagel is somewhere between 4.1 and 10.3. Does that make sense? So what does this actually mean? It means that I can be confident that for this particular supplier, and I don't want to do any name calling like Warburton or some, oh, sorry. So this particular supplier, I can expect in a bagel somewhere between 4.1 and 10.3 raisins. That is what this confidence interval actually tells me. I can't say it will be exactly what would be 6 raisins or 7 raisins, but I'm pretty sure that from this calculation here, what this calculator does, 20 raisins in 3 bagels, I'm pretty sure it is somewhere between 4.1 and 10.3. So we can head over again to the other screen. So I can be pretty sure that for this particular supplier, this supplier gives me 4.1 to 10.3 raisins per bagel. Now, recently my wife couldn't get my preferred sort of bagel, so she got supplier 2. And I counted actually 4 and 3 raisins in 2 bagels. Okay. So I've got 4 and 3 in 2 bagels. So that is 7, obviously, in 2 bagels. Now, I told you, I would like to have as many raisins as possible. Which one should I actually go for? Should I go for this supplier 1? Or should I go for supplier 2? What do you think? Supplier 1. Okay, supplier 1 is more expensive. Supplier 2. But it looks like there are less raisins per bagel. Let's head over to the calculator again. And let's put that in. So here we've got, that's our supplier 2 here. And we had 7 raisins in 2 bagels. Do you see what I've done? For supplier 1, I had 20 raisins in 3. And for the supplier 2, I have 7 raisins in 2 bagels. And I get a confidence interval again. This confidence interval tells me I can expect somewhere between 1.4 and 7.2 raisins per bagel for supplier 2. Now the question is there a difference between the 2 suppliers? And this difference is given by this p-value here. The p-value actually says, it measures the difference and says, if we assume there is no difference between the suppliers, how likely would it be that we find these numbers here in the number of raisins in the bagels? So if we say there is no difference between the raisins numbers for each supplier, both suppliers produce the same number of raisins, what is the chance that we find these numbers? And the probability that we find these numbers is actually 0.19. So let me head over again to the other screen. So here we said we've got, in this case, 1.4 to 7.2. That's our confidence interval. And the p-value in this case is 0.19. Now we've got a 95% confidence interval. That means we need to set our significance level alpha, and we discussed that in the last lecture. We set this to 5%, which is the same as 0.05. And now I can say my null hypothesis was there is no difference between the suppliers. So no difference between the suppliers. And the H1, the alternative hypothesis, was there is the difference between the suppliers. And I've just indicated like that. So p-value is larger than our alpha. So 0.19 is larger than 0.05. And what did I say? If p is high, do we reject or not reject the null hypothesis? H naught can stay. Yes, if p is high, H naught can stay. So we do not reject the null hypothesis, and we actually say there is no difference between the suppliers. Look at that. You told me I should go for supplier 1. But that would have been a mistake. Supplier 2, who is actually cheaper, has probably same number of raisins in the bagels. Did you see how I did that? So when it says in this calculator number of days, it actually means the number of sort of the time interval. So when we have 7 raisins, that's the count of the events in these 2 bagels, right? If I have just, 1 bagel and I measure 5 raisins in 1 bagel, I would put in the calculator 5 for the number of events, and under the days, I would just simply have 1 because I've got 1 bagel. And the upper and lower bounds is actually exactly what the calculator already gives you. This would be here the 1.5, that is the lower bound. I can expect at least 1.5 bagels, 1.5 raisins, and probably no more than 7.2. No, I'm afraid I don't. So this is the lower bound and this is the upper bound. And the calculator gives you that straight away. Let me show you. The calculator gives you that straight away. You see here, This is the lower bound, and this is the upper bound. Lower bound for supplier 1, upper bound. Does that make sense to you guys? So in this case, the events are the raisins, and the number of days is the number of bagels that I look at. Okay, happy with that? So now you can do, without any problems, all these Excel things, or all these count things. And there should be no problems for you. However, I think it's a great website. There is a way you can do it by hand, these calculations, this upper and lower bound. I deliberately don't show you that because why would you do it if you've got such a fantastic resource like this website? Although I agree, it's a little bit confusing. If this came up in the exam, I would not ask you to do it if you didn't have the resources. As long as that website is available, yes, it should be accessible. However, because it's not terribly, intuitive, I'm thinking of writing a similar calculator myself. Maybe when I've got a little bit of time, then I will do that, where it gives you actually the a little bit better understanding and maybe a little bit of tutorial to it, but I need a little bit of time for that. Yeah, it's another 3 AM, yes, indeed. And the link to this calculator is this Evan Miller's, and thank you very much for posting it, Ellie. Make a bookmark of that. I think that's definitely a good thing. Now, what I want to do is I also want to introduce you to yet another distribution, and that is what is called the binomial distribution. Have you done that at school? Binomial. Some people might have done it. Now, the classic example for binomial is just simply the coin flip, isn't it? Coin flip. Because for a binomial, the conditions for a binomial distribution is, again, we have count data. We have count data. So we do counts, and what we have is we have 2 categories. 2 categories. And only 2. We can do it only with 2. That's why it's here binomial. We have a fixed number of observations. Fixed number of observations. Fixed number of observations. And these observations have to be independent of each other. So, for example, if I flip a coin, the next coin flip wouldn't know whether it was head or tails. So it has to be independent, and the probability for an observation, probability is constant. The probability for this observation is constant. And there is another one which is probably not terribly well known. The number of observations, let's call this n, number of observations n, and the probability, for example, of getting hit, so that's the probability, and if we multiply them together, n times p, this number of observations times the probability should be larger than 10. And if we've got this given, then we can use a binomial distribution to do some calculations. And for a binomial distribution, you actually don't need a calculator or a website for a calculator, although it's nice in this case, because I'm going to show you what I mean by that, how you can do this calculation. So, what we can do, and you probably have done that at school with, is the coin fair? But I think that is rather boring. Instead, what I want to do is, in this case is I want to use a different example. I want to find out whether there is a gender bias in students taking bioscience degrees. Do more women than men do bioscience degrees, or is it the other way around? Or is there no gender bias? Now, I know that some degree programs do have a gender bias. So I used to do this lecture always after the psychologists finished their lectures. And I looked at the gender distribution in the psychology lectures. And oh boy, I have to say, there were, I didn't count properly, but it looked like that there was usually one or two blokes in a lecture theater with 200 female students. And I thought, wow, that's interesting. So is it the same for bioscience degrees? And what we are looking at, and I know this is probably not terribly politically correct, we are only looking at two categories. We are only looking at females and males. These are the two categories that we are doing for the binomial. I know people might now argue that, there are a lot of different genders, gender fluid, etc., etc. This is not what the binomial can actually deal with. So let's not discuss that. So the discussion is deactivated. And let's say I did at the University of Kent, I found that 60 students are female or identify as female and 40 identify as male. So I have my fixed number of counts, n equals, well, it's the sum of them, 60 plus 40 equals 100. Now I want to now find out from these data here, what is the distribution of male and female, not just at Kent, but also, let's say, in the southeast. And we assume that the southeast, that Kent, is a representative sample of the southeast. Very good question to how is this different to a Poisson? Now, with a Poisson, we did not have a fixed number. We have a fixed number here. That's the sum of the 60 and 40. In a Poisson, I said, I observe, for example, 60 raisins. But this number was not sort of fixed. So this is the main difference. Here we have a very fixed number, which is the sum of our two categories. And in a Poisson distribution, you also don't have two categories. You can do it with one category, for example. So what we can do now is we can try and figure out, let's say we figure out the proportion of female students So we have 60 divided by 100, and that gives us undoubtedly 0.6 or 60% of female students, right? So we've got 60% female, and we have 40 over 100. That gives us 40% of male students. Okay? So that is what we obviously observe. But will this be actually the same number for the universities across the country? What do you think? Will this be the same number of, will this proportion of female students be the same across the country? It will be roughly the same. Yes, you are right. I like that, Konrad. You are right. It will be roughly the same, but it will probably not exactly be the right number. It might be, you know, say 58, might be, you know, 65 or something like that. And for that, what we can do is we can calculate again 95% confidence interval. For the proportion of female students. We know what the proportion at Kent is, but now we want to calculate what is roughly the proportion for female students if we go to other universities. Does that make sense? So far? Or have I totally killed it now? So we expect probably something around, well, as I said, 60%, but it probably will not be exactly 60% if I go to Leicester or, London or something like that, but probably it will be in that range. Good. So how can we calculate this confidence interval? There is a fairly easy equation if you know what you are doing. So let's call the proportion of female students, let's call this P. That's the usual abbreviation. I know it's terribly confusing because it has nothing to do with a p-value. It's just an abbreviation for proportion for females in this case. And let's call the proportion for males. This is usually the other one that is abbreviated with a Q, and I indicate Q like that so that it is not getting confused with a 9 or something like that. So we have these two proportions, and we can calculate the 95% confidence interval. We can calculate that. And the equation for that is P. So that's the proportion of females. As we just said, that's the proportion of females. Let me write this. Let me write this explicitly down. The true proportion of female students all over the country is calculated by this equation. P prime plus minus 1.96, and that is a fixed number if we have a 95% confidence interval. 1.96 times the square root of P prime times 1 minus P prime divided by N prime. Right, there is a lot of explanation to do. Why 1.96? We will discuss this in detail when we come to the normal distribution. For the time being, just simply accept that it is 1.96 and this number does not change. Now, what on earth is P prime? P prime, and a lot of what you have done at school does not use this P prime, and you get it wrong. P prime is a number, is an adjusted number. Adjusted number. And for those who are interested in that, this is called the Wald adjustment. And what the heck is that? We said P, our ratio, we had 60 females in a total of 100, right? That was P. P prime is you add 60, that's the number that you had, plus 2. And you divide it by 100 plus 4. And the n is a prime as well. So P prime is 60 plus 2 divided by 100 plus 4. And that is the Wald adjustment. Y2, Y4. Actually, it turned out, like so many things in statistics, it turns out that it works. If you add 3 and, for example, 6 here, the numbers don't work out. And this adjustment is necessary because occasionally you might find that there are 0 students in, let's say, observed 10. If that is the case, the whole binomial would break down. But with a Wald adjustment, so if that is P, 0 over 10, the Wald adjustment gives you 0 plus 2 divided by 10 plus 4, so that gives you 2 over 14. And you can still use the binomial equation if you've got something like that. If you've got 0 over 10, it's not going to work. This one here works. So ideally, you always use the Wald equation or the Wald adjustment if you do these numbers. So what we can do now is, hang on, what is n prime? N prime is just simply the number of observations plus 4 again. So n prime in this case is 100 plus 4. Let's just simply do our calculation. So the true proportion of females, true proportion of females in our case is, we have prime. So we have here, this is this number here, P prime. So that would be 62 over 104, right? So we've got 62 over 104. That's this part here. Plus minus 1.96 times the square root of 62 over 104. That's this guy here. Times 1 minus 62 over 104. That's what's in this bracket here, divided by 104. And is it always 2 and 4? Yes, it is. It's always 2 and 4 for the Wald amendment. So this is actually our true proportion of females for all the universities that we might have. And of course, you could now try and calculate that. And if you really want to do that, you can do that. So that would give you 0.596. I have done that before the session. Plus minus, what did I get? 0.094. 0.094. That's this part here. This means the true proportion of females, this true proportion would be anywhere between 0.596 minus 0.094. That would be the lower bound. And as the upper bound, it would be 0.596 plus 0.094. That would be the upper bound. So if you do the calculation, this would give you 0.502 or 50.2%. And here this would give you, what does that give you? Oh, I can't do that in my head. No, 0, 10, 59 plus 1. Somebody help me out. I can't do 0.69. Is that right? 0.69. So that the lower bound, that is this 0.59 minus this part that I calculated, and the upper bound is with the plus sign here. Or alternatively, if you are too lazy to do this calculation, what you can do is actually, and that will be the last action for today, you can head over to, guess what? To Evan Miller calculator, but this time it's not the count data. This time you have to go to the chi-squared test. Technically, it's not a chi-square test. It will arrive at a chi-square test. But what we had was sample 1. These were our 60 females in a total count of 100 students. And this calculator calculates the lower bound 50.2%. That's what we just got. And 69.1, that's just a little bit of rounding where I made, mine was 69%, this is 69.1, this is just rounding. So this calculator gives you the proportions of the females. Now we can, of course, we can do the same thing with the males. And for the males, we had 40 in 100. And here, we also get the lower bound for the male proportion and the upper bound for the male proportion. Do you get this? So we get the confidence interval for the females and the confidence interval for the males. And now we can, of course, say, well, it would mess up, but you would find out. Well, it's good to know the maths in this case. But you see, there is a calculator, and as long as you know how to use it, I would always go the easy option. Now we can say, what is the chance that we actually get these numbers if there was no difference between the proportions, what is the chance that we get 60 out of 100 and 40 out of 100 if the proportions were the same? We get a p-value for that. Look at that. We get a p-value of 0.0047. And this p-value now tells us that sample 1, these are our females. Here in this case, in binomial, it's with a coin flip. The females are more successful. So the proportion of females is statistically significantly higher than the proportion of males. But I really like this. Females, sample 1, is more successful. So with this and the tutorial, you are now ready to do task 3 of the practical. This p-value is low compared to the 5% alpha that we set, because we've got a 95% confidence interval. P is low, H naught must go. It is unlikely that we see these numbers if we assume that there is no difference between the two proportions. So with that, I leave you alone. Thank you very much for watching, and I hope you enjoyed it and you learned something. And tomorrow I see people for BI 301 again, where we are going to do, well, I haven't decided. Have a lovely afternoon and don't do anything I wouldn't do. Be good. Cheerio. Bye-bye.